The Big Bang. It's been fun, but the cosmology community is in a bit of a tiz-was just now because the pictures from the James Webb Space Telescope are contradicting their model of the expanding universe. They don't show the early universe as they expected, as they envisaged it, with very few stars, certainly no galaxies. Instead, we're seeing mature galaxies that would have taken billions of years to develop. So I'm going to look at why they thought they'd be able to see this early universe in another video. Well, we're not seeing the early universe because there wasn't one. There wasn't a Big Bang. The theory is nonsense. So I'm going to show you why. The theory says the universe is expanding away from a minuscule starting point, and distant stars are moving away from us at high speed. The further away they are, the faster they're moving. So the expansion is accelerating. So the evidence to cite for this is redshift. Okay. So when a star emits light, some of it is absorbed by elements within the star, and each element absorbs at a specific frequency, which gives rise to dark lines in the spectrum, which we call absorption lines. In the light from distant stars, these lines are shifted relative to their positions in light from our sun. This shift is to longer wavelengths, i.e. towards the red end of the spectrum. The theory says that this is due to the stretching of the wavelength of the light due to the star's motion away. So I've clarified that, just in a diagram. So there we've got a star moving away from us. Right. That's us here on Earth. Okay. That's the sun. Okay. So the star's moving away and its light is stretched because of that. So the absorption line, see, is at a longer wavelength. Okay. Compared to the light from that same element in our sun. Okay. Now, according to accepted scientific wisdom, light has the same velocity c for us and for any observer, whatever the motion of its source. So the stretched light from this star has velocity c for us, even though the star is moving away with velocity v. So you might expect it to be, for the moving star, you might expect the velocity of its light to be c plus v. But no, it's got to be c for an observer at the receding star, just as it is for us. It's almost as if the star's moving in a medium centred on us. You could think of it that way. So the velocity relative to the receding star, he would measure that, and that is presumably catered for, accommodated by special relativity, with his clock running slower and his measuring instruments being contracted. Length contraction, yeah. Okay. So, whichever direction we look in, redshift is the same in all directions. Our sphere of vision of the universe, redshift is the same from equidistant stars, whichever direction. So that's us at the centre. Got 4 stars there moving away with equal velocities, redshift equal for all 4, okay? So we're at the centre of this redshift phenomenon. But we can't be at the centre of an expanding universe, can we? I mean, surely we would have moved away from the origin of the Big Bang in the 13.8 billion years of its existence. So if we take those 4 stars again, with us at the centre, so there we are, there's the centre, the Big Bang there, expanding, so we're moving away, and this would be the direction of movement of the other 4 stars. Now you see that they cannot be moving away from us with the same velocity. That one, because of its direction, would be moving away from us much more slowly than that one. Remember, that one's further away from the centre, so that one will be going much faster as well than the rest of the stars, okay? So, well, that's pretty obvious. So, the redshift, if you accept that diagram as what's going on, the redshift should be different in different directions. So surely that disqualifies the whole theory, doesn't it? Well, in this amazing, mysterious, expanding universe, there's a solution. There's an answer to that objection. That representation is just too simple. It's the traditional way of looking at things. So you see, just before the Big Bang, everything and everywhere that we see now was in an infinitesimally small place. So you could say that everything was at the centre. Okay? So everything, all the stars and all the points in the universe that we see now, has retained this inherent centrality. So every location will have the same view. Everywhere you go, you would see an equality of redshift because we're all at the centre, wherever we are in the universe. Well, it's a nice idea. It's ingenious, isn't it? But I think we're just supposed to accept that and say, oh, fine. I don't accept that. Nonsense. I don't know what you think, but just to reinforce my point of view, take 3 stars this time, 3 observers on 3, or close to 3 stars, a red, a blue and a green star. Okay. Say we're on the red. Okay. A bit dark, isn't it? We're on the red, so we see the green star moving in that direction. Are we supposed to? Okay. An observer near the blue star would see the green star, should see the green star moving in that direction. Okay, and the same applies for all 3, okay? So those 3 viewpoints are clearly at odds, aren't they? There's no way you can reconcile that, as far as I can see. But the thing is that all these 3 viewpoints they're equivalent. The principle of equivalence says that every viewpoint has the same should be valid, equally valid. Okay. I just can't see how we can reconcile that at all. Just consider the situation again for red and blue. For us, the red star, blue's radiation is stretched. For the guy at the blue star, the radiation from our sun, the red sun, is stretched. So for us, the wavelength in our direction, why would it be different from the wavelength in that direction? So I think that's it, that's the argument basically, but I just want to have a little digression regarding the special relativity thing, because I don't know, somebody might argue that the slowing of clocks and contraction of measuring instruments due to motion of special relativity might somehow resolve these contradictions. I think it's obvious from what you just seen. There's no argument can resolve the lack of equivalence of systems that I've just shown, that I've just demonstrated. If you need convincing that there's any merit in that argument, the truth is that special relativity, in any case, it fails spectacularly when applied to the situation of a receding star. Like, we insist that the light from the receding star travels at the same speed as our local light, and that it travels at that same velocity as measured by someone at the receding star. Light must always travel at 300,000 kilometers per second for everyone, everywhere, regardless of motion. Special relativity says this is achieved by the slowing of the moving observer's clock and the contraction of his length measuring instruments. This would mean, as you can see here, that for him a photon would travel a greater distance in a lesser time than we would measure it. Okay, that's us. This is our measuring instrument, measuring the distance that the light has travelled, and this is our clock measuring the time. No, that sorry. that's the time as he measured it. Yeah. And you can see that. Sorry, that is the distance with his contracted measuring instrument. The divisions are closer together. So that a photon for him will have travelled further in a shorter time. So he's going to calculate the velocity to be much higher than c. So it doesn't work, I'm afraid. It fails as special relativity. I've shown about this in a previous video about the mathematical trick of special relativity, whereby the Lorentz transformation equations adjust the distance and time measurements for a photon's out and back journey, so that two different velocities relative to a moving observer moving in the same direction as the photon, two different velocities for the out and the back journey of the photon, those two velocities are converted to a single velocity, i.e. c. Unfortunately, in our case of an expanding universe, a receding star, photons are only coming one way, right? So that's why relativity failed. Special relativity fails spectacularly. Oh well, there, look, the Big Bang have deconstructed, debunked it. That's it, done and dusted. I think the universe is probably static. I don't know. Yeah, more or less. And this red shift is just due to a loss of energy of the light. Tired light, loss of energy, stroke, loss of velocity possibly. That's for another time, though, another subject altogether. Anyway, as I said, I'm going to do another video looking at the expanding universe model, a bit more detail, because I want to show why they thought that we would be able to see that early universe. Because I think it's an interesting case study of the psychology involved there. Don't they see these simple, obvious objections that I've just laid out? Didn't they want to see them? What were the motives? Anyway, I'll go into that in the next video, so if you think it's worth your while, you can watch that one.